Hello and welcome everybody. My name is Mike Grützmacher from Mentor Graphics, and in this short video we will have a look on a CFD heat exchanger simulation with porous media as surrogate material. Heat exchangers are used in all kinds of industries. In the automotive, for example, as air-water radiator, for engine and oil cooling, as an intercooler, or for air conditioning and so on. This is a representative example. To increase the heat exchange area, plate fins are arranged in the air side. We will use the porous media capability as a surrogate material because a detailed simulation of these thin structures would result in an extensive calculation time. The inside flow medium is water. The water side has two passes in a U-shape, and the outside medium is air, which is cooled down in this example by the cold water. For this example, we have four variations of the fin geometries. The first step is to characterize the fin geometry examples in terms of pressure drop and heat transfer rate. Here we can see our fin geometry, and we will use the FLOEFD parametric study to run a range of inlet velocities. From the parametric study we get quickly the pressure drop and the enthalpy difference, from which we calculate the heat transfer coefficient depending on the mass flow rate. From the list of available parameters, we select the inlet velocity and quickly set up our calculation points for the velocity. The output parameters are our goals, and we want to determine the solid average temperature of the fin, the mass flow rate, the enthalpy difference and the pressure drop. The results can be exported to Excel later. The results for our four different example variations are shown in these charts. On the x-axis the air velocity is shown, the y-axis shows the heat transfer coefficient in the first chart and the pressure drop in the second chart. Where applicable, the same characterization is done for the crossflow conditions. Let's have a look on the calculation setup for the overall heat exchanger. The hot air is on the outside, shown by the red and blue arrows, and cooled down by the cold water which is flowing through the interior region inside the plates. Instead of the complex fin geometry, we apply the porous media. The characterized curves for the pressure drop and the heat transfer coefficient in combination with the geometric sheet metal properties can now be used to define the porous media properties in the engineering database of FLOEFD. And we use the parametric study again. In this example, we want to determine the air outlet temperature and the pressure drop for several volume flow rates at constant inlet temperature. We select the inlet volume flow rate and quickly set up the calculation points. And our goals as output parameters, here air outlet temperature and pressure drop for the shown scenario. One engineering goal might be to ensure a specific air outlet temperature for given volume flow rates. This can lead to an operational diagram as shown. This chart shows also the result of a variant without any sheet plates, which of course shows the highest air outlet temperature. The parametric study enables a fast characterization of the porous media. This approach decreases the calculation time and enables to create the shown operational diagrams much more efficient. FLOEFD allows an efficient and engineer-suitable simulation process. CAD embedding allows automatic recognition of fluid regions. The fully automatic meshing of the complex geometry happens directly on the CAD model, for example in CATIA V5, in PTC Creo, or in Siemens NX. The parametric CAD model allows rapid geometry changes that can also be used in a parametric study. Thanks for listening and have a nice day.